So I was told that I have to speak into the microphone. That's true. I have a tendency to wander. Can you hear me? I have a tendency to wander around when I'm lecturing and giving presentations, so I'll do my best. So if you watch this online or wherever you watch it, it'll be in and outs, but so I'll try to keep them to a minimum. So the name of my talk today is QCD and the strong interaction, which has changed from the original version, which was TBA. I thought that was uninteresting, so it was actually changed to QCD and the strong reaction, and I don't know what the strong reaction is in QCD, and so finally we got it right, QCD and the strong interaction. And I don't know if anybody recognizes this. This is a Kandinsky. He was maybe you art people. So anyway, okay, so welcome. What I'm going to talk about today, give you some kind of motivation for strong physics, what exactly strong physics is, why we believe that there is strong physics out there, talk about an early model to describe it, then move on to the fundamental theory, which is different than a model. Hopefully I'll draw that distinction for you, which is called quantum chromodynamics, and I will not say that probably ever again, today at least. From now on it's going to be QCD. Talk about how you solve the equations of QCD. You can solve them two different ways, and we'll go into that. Finally, a little bit of why you solve the equations of QCD. You know, what kind of things we can calculate, et cetera, et cetera. Okay, so first of all, particle physicists. What do particle physicists do? And you hear a little cartoon of Einstein. I guess he wasn't really considered a particle physicist. He was just a physicist of all trades. Is that something? Anyway, what kind of questions do we ask? Well, what are the elementary constituents of matter? And what are the forces that control their behavior at the most basic level? Now, I guess this probably isn't really exclusive to particle physicists. I would say this is maybe exclusive to, well, anybody, at least anybody doing physics. But today we're going to focus on the particle physics aspect of these questions. So, where do we begin? Well, at the beginning, a couple thousand years ago, we thought there were four elements: earth, air, fire, and water. We quickly learned that there were more elements, for example, sulfur, salt, mercury. And then as we probed deeper and deeper, we found there chemical elements: hydrogen, helium, lithium, beryllium, etc. And then things started to not quite make sense in the world. We found that the chemical elements were not enough to describe the world, and so we found that there was some sort of deeper structure. We knew that that an atom, while it was neutral, was composed of charged particles, and those charged particles, the electron and the proton, and we thought that that could be the end. But then the neutron was discovered about 100 years ago, and more particles, subatomic particles, were discovered. So the number of particles boosted up here. Finally, we found that those subatomic particles had some internal structure to them, and so then you come back down, and right now we think there are 14 particles, the 14 fundamental particles. 6 types of quarks, 6 types of leptons, and 4 of the force carriers. And as you can see, here's year 2000, and the question marks extend up to the year 2020 and beyond. So, the structure of matter, where are we? Well, this is you and I, right now. We're holding blocks in our hands. Okay, am I have a block? I don't have a block. We're holding blocks in our hands. We know that the block has some sort of structure to it. Now, whether it's a glass block, a wood block, whether it has a lattice structure or a random structure, it has some sort of structure below just what we see here in our hand. Okay, and that would be the atomic level. Within the atoms, we know that there exist nuclei, which are composed of the positively charged proton, the neutral neutron, with the electron cloud, the electrons swirling about. You go deeper, and as I said, here's the nucleus. The nucleus is composed of protons and neutrons, which I will collectively call nucleons. And then this is where it stood for, well, up until probably about 1960 or so, when high-energy nuclear physics experiments started to show some internal structure to the proton and the neutron. And we can actually see this without nuclear physics, and I'm going to talk about this in the next couple of slides, why there must be some sort of internal structure to these particles, why there must be another force going on instead of just gravity and electromagnetism. And finally, the internal structure of the proton is composed of quarks and gluons. Quarks interact via the exchange of gluons. Now, what's the level we're at here? Well, if you take a meter stick, I have a meter stick? No. Take a meter stick, and you divide that meter stick into 1,000,000 pieces, right? Then you take that millionth of a meter, and you divide it yet again by 1,000,000 pieces. Then you take that, millionth of a millionth, and divide that by 1,000, and then you arrive at the size of a proton. The proton is about 10 to the minus 15th meters, called a fermi, or a femtometer. The quarks are, as far as we know, truly point particles. They have no spatial extent. And we've seen down to about 10 to the minus 18th meters. So a millionth of a millionth of a millionth of a meter is how deep we probed to try to resolve some internal structure to these quarks. And we haven't, as of yet, seen them. And it's not just the quarks. It's also the electrons and the photon. They all have, as far as we know, have no internal structure. These quarks make up the proton, of course, excuse me. And this is a artist's rendition of a high-energy nuclear physics, particle physics experiment. I'll talk about what this means. I thought it was a pretty picture, so I just put it in there to fill that spot. Pretty good job, I'd say. Fine. So, classical versus quantum. In the late 1800s, classical physics was sort of out the door. Not really out the door. Was in need of an overhaul, I guess. We found that there were a lot of experiments that were going on that didn't agree with theoretical calculations. And there's a problem with that because we want, of course, our calculations to agree with the experiment because that's why we do calculations. We make predictions, etc. And so what we found is that the rules, in quotes, of classical physics, which is, for example, if I let this drop, which I won't, Dave, if I let this drop, we can calculate how fast it's going to be going when it hits the ground. We're going to know how long it takes. Okay? Quantum mechanics, classical physics was basically extended and then violently overthrown and gave birth to quantum physics. And quantum physics is the rules. Sorry, I'm wandering away. The rules by which we do calculations, etc. They don't apply anymore to the quantum world. So we need this new theory, and this new theory was called quantum physics. So let's set up an example. Suppose that we're at a baseball game. I see the Phillies threw a new hitter last night. Excellent. Yeah. Suppose we're at a baseball game, and we're watching the pitcher pitch the ball, and we see the radar gun over here, right? And so he pitches a pitch at 95 miles an hour, right? In principle, there's no reason why simultaneously I can't know exactly how fast that ball's going and exactly where it is. We have high-speed photography. We have these accurate radar guns. So in principle, I can measure to any degree of accuracy how fast that ball is going, right, and where it is. This is not true. This is no longer true in the quantum world, right? There's something which was first derived by Werner Heisenberg when he was in his early 20s, I believe, called the uncertainty principle. The uncertainty principle puts a limit on how well you can determine observables. An observable in this case would be position, and this P here is momentum. So if this sigma here, and I promise I won't put many equations in here. This is not an equation. It's an inequality. Yeah. This is the uncertainty in position. So it's how well we know position. Right? If we don't know it very well, then this is going to be a large quantity. This is the uncertainty in the velocity or the momentum of the particle. Okay? This inequality puts a constraint on that. It must be equal to it must be greater than or equal to this constant here, which is it's basically Planck's constant. It's a very small number. So, for example, if we know the position very well, then we don't know the momentum very well. Right? But this is only applied to quantum particles. And actually, maybe the biologist can correct me if I'm wrong, but I remember reading that you can actually see this on the scale of a virus, which I don't know the size of a virus off the top of my head. But if you look through a microscope at a virus, you see it wiggling. Now, with very high-speed photography, you can actually take a picture of the virus, but if you just look at it with the naked eye, we can't actually resolve it because of the uncertainty principle. And basically, to understand what's going on here, if you want to look at an electron, which is a very small particle, we know that quantum mechanics tells us, at least, that light carries momentum and energy, right? So if you guys can see me here because the light is coming from the lights up here, bouncing off me and hitting your eyes. Well, that's the same way we look at an electron. We shine light on it, okay? And so basically light, we know, has a wavelength, a frequency, etc. It can be shown that the energy associated with light goes as inverse of the wavelength, right? So if I want to resolve a very small electron with a wave with light, right? I need to look at very small wavelengths. But when I look at very small wavelengths, that's high momentum, high energy, and so what's going to happen is I'm going to kick the electron out of its current momentum, right? So that's why I can know the electron's position very well, but I can't know its momentum, right? And vice versa. Okay? Good. So, and here's a nice cartoon, because you always need a cartoon in talks. How do we do it? Well, we apply the same ideas to quantum physics as we do to classical physics. We look for conserved quantities. So, for example, if you ever took any kind of high school physics, you probably dealt with momentum conservation. Momentum conservation tells us that you have a certain momentum of a particle. It's just a property, a momentum or an energy of a system. Then the system undergoes some sort of changes. If you measure that momentum or energy afterwards, you're going to get the same value. Okay, so for example, right, suppose you have an unstable nucleus here, americium-241. And believe it or not, everyone has americium-241 in their house. Does anybody know where? You know. Yeah, your smoke detectors have a small amount of americium-241 to detect smoke. You put a battery, there's a potential difference across the plate, and these emit charged particles, alpha particles, constantly. And so when the smoke comes in there, it binds to the alpha particle and makes it neutral, and so it reduces the current that goes across these plates and then sets off the bell. So we all have this. So the americium is going to decay. You're going to emit an alpha particle, and if you measure the total momentum of this beforehand and the total momentum of this afterwards, you're going to get the same value. Right? That's an idea. That's what's known as a conservation law, and that's what we do in physics. We look for things which are conserved. Okay. Fine. So in nature, as far as we know, there are 4 fundamental interactions or fundamental forces. I don't like to use the term fundamental forces because I'm not sure how to describe weak nuclear forces. I call it weak or strong nuclear forces. I call them weak interactions, strong interactions. But it's the same idea as a force. You know, I'm attracted to the Earth, so it pins me down, kind of thing. Protons are attracted to electrons, etc. As far as we know, there are 4 forces. Gravity, which is described, which was first explained by Newton a couple hundred years ago. His theory was then supplanted, I guess, by Einstein's theory of general relativity. All electromagnetic phenomena are described by Maxwell's equations, and on the quantum level by quantum electrodynamics, which was done by Feynman. And then the weak and the strong nuclear forces. Strong nuclear force is the one we're going to focus on today. Weak nuclear force is extremely important, of course. It has all kinds of applications in medicine, for example. And so, yeah. So what we have so far, what we know so far, is that the standard model of elementary particle physics. And as I mentioned earlier, as far as we know, there are 16 fundamental particles. These are called the quarks: up, down, charm, strange, top, bottom. Those are the names, I think. And these are called the flavors of quarks. And I think nobody really took the Quark model seriously when it first started, and so that's why they have these crazy names, and they stuck. So yeah, these are the 6 flavors of quarks. In my research, we actually have there's a point where these actually become, I guess, degenerate and then become more of them, and we call those tastes of quarks. I didn't come up with that, but so anyway, and then there are the 6 leptons. These are called the neutrinos, and then the electron, and heavier versions of the electron, and the mu and the tau. And these are the force carriers. So 2 protons, in quote, feel each other or experience each other's presence by the exchange of a photon. All right, that's called a gauge theory, and that's how these particles feel each other. the gluon is the force carrier of the strong interaction, and these are the force carriers of the weak interaction. In all of particle physics, the gravitational force is neglected. It's so weak, relatively speaking, that we don't have to consider it at all. Okay, so I'm not going to talk any more about gravity. Sorry. All right, so an example, nuclear forces. Probably most of you have heard of beta decay. Beta decay is when within an atom, within a nucleus, you have a neutron converted to a proton with the emission of an electron and an anti-electron neutrino. Coming back to conservation of energy, this particle here was first proposed by Pauli because the energy before did not equal the energy after, and he knew conservation of energy, at least we thought conservation of energy was true, and so he proposed the existence of this tiny small particle called a neutrino, little tiny one I think is what it means, and that was a triumph of conservation of energy, and people looked for it, and eventually it was found. Okay, so what happens in this? Well, here you have a really hard to see nucleus. You have carbon-14, and carbon-14 undergoes beta decay, beta minus decay because it emits an electron, and transforms into nitrogen-14. So it starts out with 8 neutrons and 6 protons, ends up with 7 neutrons, 7 protons. You emits the antineutrino and the electron, and then beta plus decay is when you have carbon 10 change. You have a proton gets converted to a neutron with the emission of a neutrino and a positron, which is an anti-electron. And what's going on at the more fundamental level, you have a neutron propagating here with these quarks inside of them. One of the quarks spontaneously gets converted to a different flavor of quark, and it emits these other particles, and this particle is unstable and decays. And so this is a basic reaction in nuclear physics. Okay, this is, beta I think is used for some sort of radiation therapy. Okay, that's all we're pretty much going to talk about for the weak force. The rest of today is going to be spent talking about the strong nuclear force, which is what I deal with in my research. Yeah, so again, another cartoon is necessary at this point. All right, so the big question is, why do we suspect that there is another force out there beyond gravity and electromagnetism? Right? After all, the world was fine, which is 2 forces. Why complicate it more? Well, there's stuff out there that makes us think that maybe there's more structure to the world than just gravity and electromagnetism. So here's the question: we know that protons repel each other. So why is this beryllium nucleus stable? Why doesn't it explode? Why doesn't it blow itself apart? After all, we know the neutrons are not charged. We know the protons have positive charge, so if electromagnetism is the only force at work here, and we know that gravity is, 20 times weaker, I think, than electromagnetism, something like that, maybe not quite that much, why is beryllium a stable nucleus? Right? And the answer must be, of course, that there's some other force at play there. Right? There must be some other force that's binding these together that's stronger than electromagnetism. Okay, and that is, of course, the strong nuclear force. Another way we can see it, and this is a classical physics experiment, is we know a neutron has no charge, right? So if a neutron enters a magnetic field, okay, a constant magnetic field in space, this is the neutron, and this is something called the magnetic dipole moment. It basically establishes an interaction with the external field of the neutron, the external magnetic field. So if it comes in here, it's going to be undeflected. We know that because the neutron has no charge, right? If the neutron had no substructure, right, it was not composed of smaller particles, smaller charged particles, right? If I introduced a spatially varying magnetic field to this region, okay, if the neutron had no internal structure, there would be no deflection, right? If there is a deflection, we know that there must be some internal structure and that there must undergo a slight rearrangement of charges here, and the force on the top must be a little bit greater than the force on the bottom. Okay, and that's actually what was seen experimentally. You have a spatially varying magnetic field where the magnetic field down here is stronger than the magnetic field up here. No, the other way around. It's weaker, stronger. And so when the neutron enters this region of space, right, the force up here is going to be slightly less than the force down here, and so we're going to have a deflection. This is purely a classical physics experiment, but it shows that there must be some sort of substructure to the neutron. Okay. Now, skip ahead about 30 years and introduce Murray Gell-Mann. Murray Gell-Mann, he's still alive. He's 81. He's won the Nobel Prize back in the 60s for what's called the Quark Model, which we'll talk about. But we knew that there was the neutron, the proton, and the electron. Okay? But then when people started to ramp up these particle accelerators to higher and higher energies, what we found was that there were lots and lots and lots of particles produced. Okay? And that has affectionately been called the particle zoo. This is actually a technical term. Everyone in particle physics knows what the particle zoo is. And this is just an example of high-energy physics experiments where particles are coming in. You see the swirling here because the particles have charge and there's a magnetic field present. Okay, but that's called the particle zoo. And here is just, I don't know how up-to-date this is because they're discovering new particles very frequently. But this is just an example. This gives you an example of how many particles there just are out there, how many subatomic particles are out there. And there will be a quiz at the end. See who can name the most. Okay. Speaking of Murray Gell-Mann, Murray Gell-Mann was, so in cataloging all of these particles, all of these subatomic particles within the particle zoo, he found that if you arrange the particles according to some number associated with it, this is called the strangeness number, and it doesn't matter. It's just a property of a particle that we don't really care about now. But if you arrange it according to the strangeness and the charge of the particle, he found that these particles form these interesting geometric patterns. Right? And this here is called the baryon octet. I think it's called the octet because there's 8 particles. Oct, right? I think so. That's a joke. Okay. Yes, I know oct. Yeah, so this is called the baryon octet. Over here, this is called the baryon decouplet. Okay, and he found, again, you arrange according to this strangeness, this particle here, and the charge here, he found that if you plot them there, you get this interesting geometric pattern. What's interesting is that the baryon decouplet only had 9 particles. This particle was actually missing at the time that Murray Gell-Mann first did this. But what Murray Gell-Mann said was that, all right, I think to complete my triangle here, I need to have another particle. And from his model, he predicted the mass of the particle, he predicted the charge of the particle, and he predicted the strangeness of the particle. So as a theorist, what he did was he told his experimental compadres to go out and look for this particle. He said, I should have this property. Lo and behold, a few years later, they found this particle. And that was, I believe, that was just a great story, a triumph of theory, because theorists sometimes get a bad rap. But anyway, so this was the particle. It was called the omega minus particle because it has charge -1. Okay. Yes, quarks. Murray Gell-Mann coined the phrase. Well, he called these particles quarks. He was a very classically trained in everything. I think he maybe knows everything. But he called these particles quarks because no one had ever seen a quark. Still no one has ever seen a quark. We know they're there by high-energy nuclear physics experiments. But no one's ever seen a quark. And so the line is 3 quarks for muster mark by James Joyce from Finnegan's Wake. And I've never read this. Shame on me. I know I will at some point. But quarks were evidently very elusive characters, and so that's why he called them quarks, because no one had ever seen them. So that's James Joyce. He was Scottish or Irish? Probably Irish. Yeah. Okay. So Murray Gell-Mann, he invented the Quark model. And what he said was that the proton is composed of 3 of these quarks, right? And he called them up, up, and down. And so the charge of these quarks, if we know the charge of the proton is +1, it has positive charge. The charge of these 2 particles, of these 2 quarks, is 2/3 the fundamental unit of charge, or 2/3 the proton charge. So 2/3 plus 2/3, what must then be the charge of the down quark? 2/3 plus 2/3 plus x equals 1, -1/3. Right? The charge of the down quark must be -1/3. And he said that these particles combine only in 3s to form protons, neutrons, etc., or only in 2s, right? And this is an up quark and what's called an anti-down quark. Now, without going into any crazy detail, every particle that we know has a corresponding antiparticle, which has the property that it has the same properties as the particle, except they're anti, they're reversed. All right, and they have furthermore a property that if they come in contact with each other, they mutually annihilate. All right, that's the definition of an antiparticle. Now there's more to it than that, of course, but that's good enough for us. And so what happens is, this is a type of particle called a pion, a pi meson. Pi meson is composed of an up quark and an anti-down quark. All right, and so Murray Gell-Mann did some very successful calculations based upon this simple model. But it is just that. It's a model. So it didn't work outside of certain energies, for example. And so what we seek is, as the second slide or third slide said, we want to describe the world at the most fundamental of levels. Okay? And so we seek not a model, but more a theory. Okay? And that's where quantum chromodynamics comes in. I said it again, sorry. QCD comes in. And QCD is the, and that is italicized, the theory of the strong interaction. We hope. It's still a pretty young theory, and it's been verified many, many times, but still, you can't really prove a theory. You just kind of have to disprove it. So anyway, so what happens is you have these two quarks, and they interact via the exchange of a gluon. A gluon because it glues them together. Physics, sometimes they're original, sometimes they're not. Clearly, Murray Gell-Mann did not come up with this term. And so there are, as I said earlier, there are 6 types of quarks, and there are 6 types of antiquarks. And here's the 10 to the minus 18th again, a millionth of a millionth of a millionth of a meter. We see no substructure to the quarks. How am I doing on time? How long do I have? Till 1 o'clock. Okay, excellent. So a couple interesting properties of QCD. There's something called confinement. Now, confinement is why we don't ever see quarks. We've never seen quarks in experiments. And that's because quarks are bound within hadrons. Hadrons are anything made of quarks. All right, and they're the 2 types. They're the three quark hadrons and the 2 quark hadrons. So this was this is Wilczek, Politzer, and Gross. These 2 may be reversed. Definitely physicists, though. They won the Nobel Prize back in 2004 for proving confinement, or proving asymptotic freedom in QCD. And basically, you think of it like this. We know that the force between a proton and an electron, as we move them farther and farther away, okay, the force between them, the interaction strength, goes down. And it goes down by what's called an inverse square. So if I double the distance, I decrease the interaction strength by a factor of 4. Okay? And that's the same. Electromagnetism, gravity is the same way. QCD is not, though. QCD, you can think of the quarks are, and this is not completely correct, but it's a good analogy. The quarks are basically tied together by springs. Now, we know that as you extend a spring, it gets harder and harder to extend it the farther away you get. Okay? And that's the same idea here. These quarks, see how they're pushing? We're trying to pull. These are not quarks. These are pictures of quarks. But as you're pulling them away, right, it gets harder and harder. And eventually, because the energy goes as the distance of separation, eventually you're going to get enough energy where you can actually produce more of these quarks. All right, so you can start out with 2 quarks. I separate them. Eventually, poof, I end up with 4 quarks. And we don't have, if you want to ask me about that, you can ask me about that. But the details of that are pretty technical. But I would love to spend an hour talking about it. Asymptotic freedom. Now, if you take a spring or a rubber band, I just happen to have a rubber band. I always wear one just in case for reasons like this. Right. So here is, if you guys can all see this, I'm stretching this out. Right. The quarks don't want to be pulled apart. Blah blah blah. Eventually, if I go the other way, what happens here? The rubber band kind of gets limp or loose, right? And what happens is, if I have quarks on the ends of these, they're basically free. When the rubber band is like this, they basically don't feel each other anymore. All right, and that's what is known as asymptotic freedom. And this is experimentally verified. This right here is called the coupling. This is the interaction strength, and you can see that see, this is not a distance actually. This is energy, like as far as how deep down you can probe. And so high energies mean you're probing very short distances because you can really burrow into the proton, for example. Yeah. So at short distances, at short distances, which is out here, excuse me, at high energies, right, this coupling goes down, right? At low energies, you're not really digging too far down into the proton, so you see the long-distance interactions of the quarks. And that's out here where the coupling becomes large, right? This bad, this good. Why is this good? Well, again, without getting into any kind of technical details, out here in this region, you can do calculations. You can do physics. You can take the solution and you can do what's called a perturbative expansion in this coupling, and so you can calculate term by term, and each term is less and less important. So it's like taking each term and multiplying each term by a factor of 1 over 10 to the n, for example. So first term would be 1, then 1/10, 1/100th, 1/1000th, et cetera, et cetera. Okay? And this here is basically the energy of the interaction. And we can see these two regions here. For short distances, this is basically the interaction that goes with the electromagnetism. Okay? And we know we can do calculations in the regime of electromagnetism. This is for long distances. You can see for long distances, it goes linearly, so the energy gets larger and larger. Right? And that corresponds to the coupling out here. Okay? Now, what about quarks? Well, it turns out that quarks are called, they're fermions. That just means they have a spin 1/2, which we don't need to talk about. You can ask me about it if you want to. But there are 3 types of quarks. Now, we said there are 6 flavors of quarks. Each of those flavors possesses another, what's called degree of freedom, or property called color. Right? Now, we know that there are 3 colors of quarks. It's basically a charge, right? They possess color charge, just like the electron and the proton possess charge, electric charge. Quarks possess what's called color charge, and so these quarks are permanently confined within hadrons, and they combine only in 2 different ways: either one of each, or a quark and an anti-quark. Okay, so a blue quark combines with an anti-blue, and obviously anti-blue is yellow. And here you can see how the combinations, only this overlap region here is the ones that exist. Okay, and we know there are 3 colors. And we call this the white region. Okay, we know there must be 3 quark colors because there's a particle out there called the delta ++, which is a member of the baryon decuplet, that was the upside-down triangle, which possesses 3 up quarks. Now, we know that this particle has spin 3 halves, which means that all of the spins, basically the way that the particle is spinning or rotating, it's going this direction and not this direction. We know they're all pointing up. They're all aligned to form a 3-halves spin. And so, based on that observation and something called the Pauli exclusion principle. Now, the Pauli exclusion principle says that 2 particles cannot occupy the same state at the same time. And if we've ever taken chemistry, we've already dealt with the Pauli exclusion principle. Do you remember when in Hund's rule, or Hund's law, when you had to fill in the boxes, and with the arrows up and the arrows down a long time ago maybe? That's an example of the Pauli exclusion principle. You can't have 2 up arrows in those boxes, otherwise your chemistry teacher yells at you. Right? You gotta have 1 up and 1 down. That's because of the Pauli exclusion principle. All right. Anyway, the Pauli exclusion principle applies here, and so if there was only 1 version of quarks instead of 3 colors, this would not happen. But we know there must be some triply degenerate degree of freedom, and so that was called, again, I don't know why, I just called that red, green, and blue, for lack of. I don't know why they choose purple or yellow, but anyway, how do we know the gluons exist? That was evidence for quarks. How do we know the gluons exist? Well, I don't want to go into too much detail about this, but basically what happens is here you have an electron and 2 electrons, electron and anti-electron interact. They mutually annihilate. They form a photon. That photon then produces a quark, anti-quark, and at some point this quark has to slow down and it emits another particle called a gluon. Gluon radiation, I guess you can call it. And so this gluon then is going to form more and more particles, and that's what you see here. These are called 3-jet events in high-energy nuclear physics. Now, again, there's a lot more detail to that you can ask me about if you want to. So, now to the good stuff. How do we do calculations in QCD? This here is called the QCD Lagrangian. Okay? Now, it doesn't look too bad, but it actually is. All right, maybe it does. Well, anyway, this is called the QCD Lagrangian, and this, in principle, contains all information of the theory. Right? It's just a matter of unlocking it, unleashing it, if you will. And it's just like when you solve F equals ma in classical physics. Most of you, maybe, I don't know, maybe all of you taken physics. We solve for x as a function of t. From that, we can get anything we want. We can calculate its energy, we can calculate its velocity, its acceleration, anything. All right. Same thing here. We can do all the calculations just from this quantity. Now, in practice, it's really difficult to solve. In principle, I'm done. In practice, no. There's a lot more to it. And so one of the ways we could do it is we can do the perturbative expansion I talked about earlier. But we already said that doesn't work for low energy physics. Right? So if I want to probe the long distance interactions of quarks, I need something else. And that something else is called lattice quantum chromodynamics, Lattice QCD. And that's what I did my PhD on. It was invented in 1974 by Kenneth Wilson. He won the Nobel Prize, but not for Lattice QCD. He won it for something else. I don't know. And the basic idea is that we need to put it on a computer. But back here, this equation, this QCD Lagrangian, these are continuous variables, continuous fields. Right? Computers don't think in terms of continuous fields, continuous variables. They think in terms of discrete numbers. Right? So in order to put the equations of QCD onto a computer, you need to discretize them. And so what he proposed was put the gluons, which are the force carriers, on the lattice links, all right, and put the quarks, they live on the lattice sites, and then evaluate your equation. You evaluate your equations numerically. Yeah, and unfortunately, there's a huge amount of degrees of freedom. For example, to get just how a quark and another quark propagate from here to there, you need to invert million by million matrices. Now, if you've ever tried to invert a matrix to 3 by 3, you probably want to kill yourself. Right? Imagine doing it million by million. Well, that's not for me, but it is for a computer. But it does take a long time. And so what you need is supercomputers. And this here is Franklin. It's a 40,000 core computer maintained by the University of California at NERSC, the National Energy Research Scientific Computing Center. Here, and this is the colors, I believe, of California, right? Gold and blue, yeah. And this is just an example of what we do. So this, believe it or not, is the proton. Right? This is the proton in QCD. Right? This is the box. All right? It's a three-dimensional. We do our calculations on four-dimensional lattice, which is 3 dimensions in space, 1 dimension in time. And that's what this is. This is a snapshot, a certain time, of the view of the proton. And you can see the proton is basically built of not just 3 particles, but millions and millions and millions and billions of particles. You can't really count them. Right? And they're constantly bubbling in and out of existence. Right? That's what the proton is. Yeah, and so even for my dissertation, I ran on this computer a lot, and I ran on a couple other computers, and it still took me 2 to 3 years to calculate, to do all my calculations. And that's using parallel jobs as well. So it really takes, it can take a month to get a single number, which is not good for a PhD. Now, what kind of things can we calculate? Well, there's one interesting thing we can calculate called the Hadron Polarizability. And the Hadron Polarizability can be likened, I guess, to the atomic polarizability. We know that the nucleus is surrounded by the electron cloud. Right? And without any kind of field present in the background, the electron cloud is just going to chill, just hang out. However, if we introduce an electric field, let's see, this would be the negative end, this would be the positive end. If we introduce an electric field out here, okay, the electron cloud is going to be deformed. It's going to be warped. All right? And we can actually measure the degree or the amount of deformation, and that gives us information as to the structure of the atom. Right? We know that because this is very easily deformed, there must be a lot of empty space, which we've been told for a long time. But this is one way to verify that. Yeah, so what we do is we do it for the hadrons. So we measure the stiffness or the rigidity of a hadron. Okay? And we find that the hadrons are very, very, very rigid. It takes a huge field, a huge external field, to deform a proton, for example. In experiments, you can do you do Compton scattering experiments in which the electric field of the photon. Compton scattering is basically you have a photon come in, it hits a particle, for example, a proton, and it kicks the proton this direction, and then you have a scattered photon. And in these kinds of experiments, you can show that the cross sections, the amount of particles being scattered into a certain angle, depends on the polarizability, on these polarizabilities here. Yeah, so I think that's enough physics. I believe I'm done. Almost. One more, sorry. And how do we do it? Well, I use something called the background field method, and one of the guys on my committee actually invented the background field method. So lucky me. So anyway, basically we introduce the magnetic field onto the lattice, and the mass, well, actually the hadron mass will shift a bit, and we measure this mass shift and we attribute it to the polarizability. And this is basically the energy shift or the mass shift, and we do some sort of expansion, and we look for these quantities, the magnetic moments, the dipole moments, and the polarizabilities. And they give us information as to the structure of the interaction, the strength of the interaction. Okay? And now I'm done. Thank you.